Example 5 for section 3.2, graphing rational functions. Write an equation for the rational function shown below. So let's start by looking at some of our characteristics here. We've got an x-intercept at -2. We've got an x-intercept at +3. So based on those x-intercepts, that's going to help us know about our numerator. So the numerator would come from the zeros -2 and +3, which means we would have x plus 2 and x minus 3. Alright, next let's look at our vertical asymptotes. We have vertical asymptotes at -1 and +2. That tells us our denominator is at x minus 2 times x plus 1 to get those numbers where the domain doesn't exist, where it would divide and make it 0. Now, we have two complications with this being the correct answer, the numerator and the denominator. And that is, right now, the degrees are the same. And if the degrees are the same, the leading coefficients are 1, and the horizontal asymptote would be at 1. But it looks to me like there's a horizontal asymptote maybe at 0. Like, this piece is kind of following 0 right there, and this piece seems to be following along 0 right there. If it is at 0, that means x-intercepts are crossing both. Both x-intercepts are crossing that horizontal asymptote at 0. But obviously, the asymptote is not at 1. The other issue here is that we've got this thing right here, which means we have a multiplicity, an even multiplicity on our asymptote created by the x minus 2, so that needs to be a square for that to work. Okay, so based on that, we would have degree on the top lower than degree on the bottom, which would give us a horizontal asymptote at 0, which I think is more accurate than the horizontal asymptote at 1. Alright, the next thing we need to do is look at our y-intercept, and we need to use what we know so far to help us predict a y-intercept at -2. So let's put what we've got together so far, like x plus 2, I'm going to use a different color, x plus 2 times x minus 3 over x minus 2 squared times x plus 1. Now here's the thing we don't know. We need to know if there's a different leading coefficient here. We need to know if this asymptote really is at 0. Oh yeah, I would assume it is because our degree at the top is less than the degree on the bottom. I forgot, we already established that, right? So y equals 0, we've got an asymptote there. Okay. We don't know if there's some value in front of this, changing the stretch compression stuff to make sure that we get a y-intercept of 2. So remember, in order to get a y-intercept of 2, we plug in 0 for our x's, and we set that, and then we solve it, and we find the answer. Well, in this case, if we already know that the y-intercept is -2 when we plug in x's, I don't feel like I'm organizing this as well as I could. So a times 0 plus 2 times 0 minus 3 over x, no, that should be a 0, 0 minus 2 squared times x plus 1. All of that times a should equal our y-intercept at -2. Because remember, the way we find a y-intercept is to plug zeros in for all the x's, work it through, find the y-intercept, right? Okay, let's go ahead and simplify this. So we'll have a, and then we have 2 and -3, so a times -6. Then on the bottom, we have -2 squared, which is 4, and 4 times 1 So we end up with negative 6a equals, and I'm going to cross multiply to solve this. So negative 6 times a divided by 4 should equal negative 2. So that means negative 6 times a should equal negative 8 when we cross multiply that. So a should equal negative 8 divided by negative 6, which is 4/3. Alright, we are done. We found our a value, but instead of putting the 4/3 up on the top, since our whole thing is a fraction anyway, we can just write it with the 4 on the top and the 3 on the bottom. So here's our final answer that should get this graph. We can check it with decimals. So 4 times x plus 2 times x minus 3 over 3 times x minus 2 squared times x plus 1. Ta-da! That should be the equation for our graph that will give us the correct x-intercept, the correct y-intercept, the correct asymptotes, and the correct end behavior here with our multiplicity.